In this problem, they're asking us, where is it, that a bar of 30 millimeter diameter, so this is a round section here, or I should put it here, round section, is subjected to a pull of 60 kilonewtons. Actually, I should write this one here so we can see that this is going to be subjected to a pull of 60 kilonewtons. And this is happening also in this direction here, 60 kilonewtons. Then it says, the measured extension on gauge length is 200 millimeters, meaning that's kind of the original configuration, the original length. So it's kind of changed or expanded or extended 0.1 millimeters, which is this one. And well, while it is kind of extended, then there is a reduction in diameter, which is the 0.04 millimeters. I just marked here 0.002, which is just one side, but two sides makes up for this 0.004 millimeters. Then they are asking us to calculate the Young modulus, Poisson's ratio, and bulk modulus. Also, this is a simple problem that requires only the introduction of values into a formula, and that's it. So it would be pretty convenient to write down here. Let's start with part A, just the formulas that we're going to be using. So the first one is Young's modulus. Here, Young's. Here it is, modulus. And the formula for this one is, it's going to be as specified. I'm going just to write it. It's kind of, what is the tensile stress here that is applied on the specimen divided by the longitudinal strain. This is what I showed in the slides. Longitudinal, let me put a longitudinal strain. Here it is. So if we want to know how much is the Young modulus of this material according to the actions and responses on it, then we just need to calculate a couple of things. Tensile stress and longitudinal strain. Let's go for the first one. Tensile stress, I'm going to call it like sigma. Yeah. So this is going to be tensile stress, this deal is going to be this one here. It's going to be what? Well, we have a force, and that force is applied on an area. So that's going to be just the force. You can call it P, you can call it force. Let's call it force applied on the area. So what's area? This transversal area of this round bar. So we have the force here. We need just to calculate how much is the area of this transversal section. Let's do it in the color. So the area is a round section, so this area is going to be as simple as pi divided by 4 times the diameter square. So that's going to be pi divided by 4. The diameter is 30 millimeters, the original one, yeah, not the modified one, like this. Now, if I make the calculations, take the calculator here, let's call it A. It's going to be equal to pi divided by 4 times 30 square. It's going to be 706, put it here, 706.85. What's that? Square millimeters. Then I got this one here. Then the tensile stress is as simple as substituting this value in this formula here. Well, not just the stress. This is what we're going to do. I'm just going so fast ahead. So the tensile stress is going to be the force applied on the specimen, which is 60 kilonewtons. I'm going to put it like this, newtons, and then to use the proper units for our case, and this is going to be divided by 706.85 square millimeters. And that's going to be equal to what? Let's do it. We have 6,000, or 6,000 divided by 7. Actually, I'm just going to write A. And that's going to give me 84.88 here. 84.88 newtons per square millimeters. And I have another piece of the puzzle here. Then let's go to calculate the longitudinal strain, and I'm going to call it like we have been calling it in the slide, like, let me change colors. This one, E. Yeah. How much is that? Well, the longitudinal strains, we know that is the change in the length divided by the original length. So that's the definition of that strain, which is the change, the rate of change of that length. So this is going to be what? It's going to be, we can call it like this, if this small part is actually the variation of the length, and this whole part is the length, then the strain is going to be defined as this. So what is this? It's going to be 0.1 millimeters, and then divided by this 200 millimeters. And we know that strains is not deformation, it's just a rate of deformation, kind of how things deform, meaning that this is going to be equal to what? Let's put it here. Strain, can I call it like that maybe? Equals to what? 0.1 divided by 200. And that's going to give us, yes, 0.0005 here, 0.0005, no units because it's non-dimensional. Now, E, your modulus is going to be what? This result that I got here and divided by this result that I got here. So what's going to be that? Let me mark it here because this is important. I'm going to use it maybe later. And let me choose a color here, and it's going to be what was 84.88 newtons per square millimeter divided by this 0.0005, which is equal to what? So let's do it. So basically is this A divided by strain, and it's giving us 169,765. So we can just reduce a little bit that number to, let's just leave it with that 169.76 times 10 to the power of 5 newtons per square millimeters. And here we have solution A. Here it is. Now let's move to calculate what is called the Poisson's ratio, yeah, and box modulus, which is part B. So let me color here. Oh, yeah. Should I use a different color? Yes, B. Here, then this is Poisson's ratio. There it is. So what's the definition that we have given for the Poisson's ratio? Well, mu, or let's change. Let's call it like this. No, just to interchange things. So that's going to be equal to what? To the lateral strain. Because remember that in Young's modulus we talk about the strain that is directed to the line of action of the force or the loading, and then with Poisson's ratio we're talking about what's the effect of that loading on a different axis, which is typically to be perpendicular to the action line of the force. Strain then divided by the longitudinal strain. Longitudinal strain. So what's the lateral strain? Well, the lateral strain, we need to treat it as such. Let me put it here. Lateral strain is going to be equal to what? Well, how much is this change reflected on the diameter here? So if now this is going to be my L, yeah, like in this case, in the length it was the L, and then you have the delta L. So if this is going to be my new L, actually it's my diameter, and this is going to be the change, well, this times 2. That just means that this is going to be kind of my change in diameter, yeah? So to build that, this is going to be, which color I have? Yeah, it's going to be, let me call it like this, sigma t, or delta t. And this is going to be delta t times 2, just a note. Delta t divided by L, or by my d, divided by, well, we're not in that point yet. So this is this value. I want to read this. So how much is the lateral strain? And actually I'm going to call this lateral strain, just to abbreviate things. Now the lateral strain is going to be what? This one here that we have divided by the longitudinal, no, for the diameter, sorry, diameter of the bar. So let's do that. So it's going to be this 0.004 divided by the longitudinal, where is it? Lateral strain, sorry, I'm just confusing with this. So this is 4 millimeters, and then the diameter is 30 millimeters. So this longitudinal strain, I'm going to put it here, it's going to be what? 0.004 divided by 330. And that's given me 0.00013. So let me write it down here. 3 zeros. So 0.00013. Is that correct? Yes. 3. No units because this is dimension, or non-dimensional. Now we can calculate a Poisson's ratio to this upper part. Let me change this. I don't want it in red, I want it in green. And this says that Poisson's ratio is the lateral strain, that I already got it there, which is 0.000133 divided by that longitudinal strain, which is this one here, is 0.0005. And let's go to the calculator, and actually it's going to be C divided over by the strain here. I think I can put it like that. Yeah. You see how much is that? 0.26. Well, let's call it 0.266. And here is my B result. We can mark it like this. And we can mark the Young modulus also to have a reference of it like this. Now part C is with another color, is bulk modulus. Here it is. And we know that the definition for bulk modulus is a one that combines the Poisson's ratio and Young modulus together, and the definition is given like K is equals to this simple formula: 3 times 1 minus 2 Poisson's ratio, and that is it. So we have Young modulus because it's calculated here. We have Poisson's ratio because it is calculated here. So the rest of the problem is just substituting those values. So let's do it. It's going to be E 1.6976 10 to the power of 5. What is this? Newtons per square millimeters. Then divided by 3 times 1 minus 2 times, we'll do a nice bracket here, like this, 0.266. Then let's go to the calculator. Okay, it's going to be what? Modulus is B divided by 3 times 1 minus 2 times D. Yeah. Excellent. So we have what? 121,260. So meaning that K, bulk modulus, I can write it like 1.2. Yeah, let's put it in this fashion. 10 to the power of 5. Let's put a little bit more units. 1.212. Yes. Which units? Only the ones that have this Young modulus, which is stress unit or pressure unit. And that is newtons per square millimeter. And here we have our third response. Put it like this, C. To summarize or recapitulate things, so we have this problem where this is being pulled by the sides, and then as it is pulled, the original length is extended, but the diameter is kind of shortened or make it smaller. Then they're asking us to calculate three things. So we have Young modulus, we have Poisson's ratio, and we have bulk modulus. And the only thing we did was to utilize these formulas, like kind of the Young modulus is just the relation between the tensile stress and longitudinal strain. So we just needed to calculate that tensile stress and strain, which is pretty simple. All the data is given. Now for Poisson's ratio, we know that that's the relation between lateral strain and longitudinal strain. We just need to calculate the reduction in the diameter part as a rate, which is given here, and then apply the formula, and we got it done. Finally, bulk modulus is just substituting values because all the ingredients are already calculated. So this is the end of the problem, and we will see each other in the next problem.